Okay, so the chemical formula of C9H10O2, I calculated the IgD, it comes out to be 5. And if you look around 3300, we can clearly see that there is an OH bond, and we know it is not an alcohol or any type of, or an alkene, because there's no dip to tell us that it's an alcohol structure or IR. So then if you move forward to around the 1500 to 1600, which is approximately here, we know that there is a possibility of having a benzene ring there, because it is a C carbon double bonded to a carbon aromatic. And if we look at 1700, we know there is a carbon double bonded to an oxygen, which gives us or tells us that there could be a carboxylic acid, ester, or ketones, but I don't think there's the ketone. I believe it is an ester. So then if we look at around 1300 or 1000, we see that there is a carbon single bonded to an oxygen, which suggests that there is an ester or carboxylic group. And again, I believe it is an ester. So now if we look at the ppm NMR, we see that around 200 there is a carbon double bonded to an oxygen, which most likely is an ester. And then if you look around from 120 to 160, we see that there is a carbon double bonded to a carbon, again aromatic, so it tells us there's a benzene ring present there. And then if you look at around 50 to approximately 120, 100-ish, there's a carbon single bonded to an oxygen, which tells us is an ester or a carboxylic acid. Again, I'm leaning towards ester. If you look from 10 to 50 ppm, we see they both are identical. And so it is either a methyl attached to a CH3 or a CH2 attached to an oxygen. So now if you look at the HNMR, and if we look at around 9.91, we say they tell us there's one hydrogen and it's a singlet, which is true. And that is in hydroxyl group OH present there, which is attached to an aromatic ring, as we said here at the CNMR thing, that we have an aromatic / benzene ring. So that's the structure that would be attached to the ring. And then splitting, because there's a broad peak. There's a broad peak, and it's broad and like our typical peak that OH usually have. And this supports the this like explains why there is an hydroxyl group and a benzene ring attached to a benzene ring. And then if you look at 7.96, which is approximately here, we see that it is still in aromatic, the benzene ring, like aromatic region. So there is definitely, so I drew a benzene ring with two, and it's a doublet, as they said here, it's a doublet with two hydrogens. So I drew the benzene ring, attached two hydrogens to it, since it's a doublet. And then if you look at 7.4, again, they tell us it's a doublet and it's two hydrogens, which is basically symmetrical to the 7.96. So I drew two more hydrogens attached to the benzene ring, since it is still in that benzene ring area, which just proves more that there is a benzene ring present. Like it clears the doubt if there is or not a benzene ring. And if you look at around 4.14, they tell us that there's 2 hydrogens as a quartet. So to the spinning is a quartet. So to draw the structure, I drew a CH3 attached to a oxygen with 2 hydrogens attached. So like the CH2 is with the 2 hydrogens, and it is attached to the oxygen, so which again supports the idea of the CH2 attached to an oxygen, as I said in the CNMR. And then if we look at around 1.30, it says that it is a 3 hydrogen is a triplet. So we see the structure. It has the I attached that to a CH3 to a CH2 structure with 2 hydrogens attached to the carbon. And to finalize the whole thing, the whole structure, I drew a benzene ring attached to an oxygen, which is attached to a CH3, which I took from here. And then I attached a carbon double bonded to an oxygen, like the OH hydroxyl group. From here, I took that and I drew it here. So the whole structure is this. Okay. Wait, sorry, let me redraw that again. This should just be a benzene ring. Attached to an oxygen, which is attached to a CH3, which is that is attached to carbon double bonded to an oxygen, which is then attached to the hydrogen.